Hello, welcome back. This is the video on how to calculate the chi-square test of independence in R. This is following the video on how to do it in Excel and the lecture slides on where we showed you how to do this by hand. So we're going to follow up with the student internship example to determine if there's a relationship or if there's a dependency between if a student has an internship or not and if this confirms their interest in working in the particular field in which they did that internship. I'm going to coast through some of the initial data entry. We have earlier videos that show you how to do that, but I do want to confirm with you that there are different ways that we can enter the data, and all of these different ways will still give us the same chi-square test results. So the first version I have is where we enter the data in a matrix form, and it comes up with a very similar looking table to what we had in the test results, with the not confirmed, unsure confirmed, and confirmed in the rows, with the no and yes internships in the columns. Now this is a matrix. There's a similar version here where we can enter it as a data frame. So the yes and no variable become variables, and we have names on the rows, and the data is still the same there. Another way we might be able to handle this is if you had received this data and let's say it was a CSV file or some other sort of flat file, and so instead of having everything in a preformed table ready to go, you had it in column form. So we can take that data, and I've gone ahead and manually entered it in here as if we had received it in a flat file, and then you're going to use the table function to call up these two variables, the confirming and internship variables, which will then show you as vectors inside of that data frame, that data set, the same test results there. And in order to use this in a chi-square, just for sake of ease, I'm going to go ahead and save it as an object. I'm saving the bivariate table as an object. So now that I have these pieces ready to go, I'm going to go ahead and show you how this is run in the chi-square test. This is super easy peasy. So the function for the chi-square test is the same as it was for the goodness of fit version, CHISQ.test, in parentheses, place the name of the object that you're running the chi-square test on. If you don't have it as an object, like we just saved a bivariate table with the table function, you could go ahead and put that entire name in there as well. In fact, I think I'll show that for you just to prove it. So the first version was where we had the chi-square test as the matrix form. And it shows us in our results that the chi-square test output is 2.4976 with 2 degrees of freedom and a p-value of 0.2868. Given a little bit of rounding, this matches exactly what we found when we did it by hand and when we did it in Excel. Note, in R, we actually get the chi-square approximation warning, which I told you about in the lecture components. This has to do with that soft rule of how thinly distributed this is across the table. Now, it's not very thinly distributed in this particular case, but we have a small sample size. And so it's flagging us because of the small sample size that we might be warned about. We have two cells that have less than 5 values in them each. I'm going to go ahead and run this again on intern 2, which was the data table that we have stored as a data frame, and we get the same exact results. No surprise. I'm going to run it again, chi-square test, on the intern.table. This is where we had the bivariate table, as if this was in a long form data set. I'm going to run that, and again, it gives us the same results. Just for the sake of completion here, I'm just going to go ahead and say, if you didn't save that information, that bivariate table, as an object, I'm just doing a little copy and pasting here, you could do the chi-square test on the table function that contains your two variables, and it will give you, again, the same exact test results. Now I'm going to go ahead and store this information here, chi-square test, as an object. I'm going to call it chi.intern, and it's stored as an object. It still gives us that warning message flag. Now we're aware of why the warning is appearing here, and we're going to take the do nothing option as far as that goes. I do want to draw your attention to the fact that any of these particular tests can have attributes. Yeah, they do. And when you run an attributes command on them, it shows you the various components of it that we can go ahead and call. So when we saved the chi-square test as an object, chi.intern, it has stored things like a statistic, a parameter, p-value. Those are what are used to show you the outputs. For example, I can do chi.intern and call up the statistic, and it tells me the x-squared value is 2.49. If I was to do the parameter, this is, don't let the name fool you, that's going to give you the degrees of freedom. If I give it the p-value, that's going to give me the p-value. And then there are other names in there as well. If I wanted, in Excel and by hand, we had to do the entire expected table by hand. I can actually do chi.intern $expected, and it will generate for me the expected values that we can see. So if you want, you could double check the work that you did in Excel. And that's how to go ahead and do the chi-square test. Moving from here, I'm going to show you how we do the effect size. So we're going to use the choice of either doing the phi or the Cramer's V. That's going to depend on the size of the table. We have a 3x2 table, so we're going to use the Cramer's V. Cramer's V and the phi, they are found in the Desk Tools library, which I'm just loading up there. And it's the Kramer V, capital C and capital V on our object. And it tells us that it's 0.2751105, or just rounded 0.28. And again, if you're looking at my code, why did I have Desk Tools : Kramer V? I just had it in there to be specific in case there's another library I had loaded that had a similar Kramer V function. It can happen. If we want to do it by hand, you can do the formula SQRT for square root, the chi-square statistic we obtained, divided by the grand total of our table, plus k-min, where min is the number of rows or columns, whichever is fewer, in this case columns, which only was 2, minus 1 leaves you with 1. And I show it, you can do it by hand, or you can do it by pulling them up, and it gives us a very close approximation of 0.27. Next thing I want to show you is power, the power of the test. Remember, our power functions, they come from the power library, which we're going to go ahead and load up. And the formula is pwr.chisq.test, power's chi-squared test. And in there we have several elements: W, the effect size, N, the total sample size, DF, the degrees of freedom, sig level, that's our alpha, and power, what is the probability we want to have. Remember, you really don't want to have anything less than 0.8. Or you enter null. Remember, one of these 5 we're entering as null, and the analysis is going to give us those back. So the question I posed during the lecture component was, what sample size would we need if we wanted to have the same effect size we've been seeing, 0.275, with 2 degrees of freedom in our chi-square test, an alpha of 0.05, and that minimum expectation of power of 0.08. How many would we need? When we go ahead and run that, it gives us the output and shows us that n equals 127.4 n values. Now we're talking about whole people here, so we're talking about somewhere between 127 and 128. If you want to just round up for being conservative, 128 people we're going to need in order to hopefully find a test given these other test values with the effect size, degrees of freedom, alpha level, and anticipated power. Now I'm not going to go over the next set of code in detail, but I do want to show you that I'm replicating the plot just like we did it with the goodness of fit, where I'm going to show you a graphical distribution of the curve where our critical region is and our critical value. The critical value, remember the formula is QCHISQ, and if we summon that up using 1 minus our alpha and then the degrees of freedom, our critical value is 5.991, which is the same value we found in the critical value table. Makes complete sense. I'm going to go ahead and run through all of this here, and it's going to generate for me the chi-square distribution. So we see here on the plot, we have this downward sloping curve. It does not yet have that familiar bubble hump that starts to look more like a normally chi-square distribution, but that's only because we have 2 degrees of freedom. The shape of the curve changes as the degrees of freedom increase. So what we have here on the right upper end of the curve is that red shaded region, and the blue dotted line vertically shows where our actual chi-square obtained value is. The blue dashed line is not in the red critical region, and therefore we are not statistically significant. our critical value is smaller than, our chi-square obtained value is smaller than our critical value, which again is reflected in our p-value and alpha, two halves of the same coin. And this covers how to do a chi-square test of independence and interpret some of these results here in R.